Hello guys, so welcome to the course Math 151, which is algebra. So we are going to look at the outline of this course, and this course is divided into chapters, and each of the chapters will be in a different video form. So let's look at something. So with chapter 1, we have introduction to number theory, the principle of mathematical induction, algebra of complex numbers. And with chapter 2, we are going to look at vector algebra. And chapter 3, we are going to look at matrix algebra. And under that, we have some sub chapters, which is the eigenvalue and the eigenvectors. So let's look at the first number system, which is the first one we're going to talk about is natural numbers. And when we talk about natural numbers, they actually start with what? 1. So the set of natural numbers or counting numbers is 1, 2, 3. And this 3 dot means that it's infinite. And the natural numbers are closed. Let's take note of this. Natural numbers are closed under addition and multiplication. Addition and multiplication. And let's try and prove the reason why natural numbers are closed under addition and multiplication. So let's try and explain. So first, let n. So normally with natural numbers, we represent natural numbers using the letter capital N, right? So whenever you see N, capital N in number theory, you know that that letter represents what? Natural numbers. So then we are going to prove it, why it's closed under addition and multiplication. So we have an element which is m and n. Let it be an element of natural numbers. This means that when you multiply m plus n, it should also give you an element which is in the natural number. And also when you add m plus n, it should be also an element from what? Natural number. What it means is that when you take any member or any element from the natural numbers and you add them, you should get another natural number. Or when you take any natural number and you multiply them, you should get what? A natural number. And that's very true, because when you take 2 plus 3, you get 5, which is a natural number. And when we take 2 times 3, you get 6, which is also a natural number. That's why they are saying that it is closed under addition and multiplication. Now, we have some properties under natural numbers, and let's break it down. So the properties are categorized into the addition property and the multiplication property. So let's look at the first one. The first one we're going to talk about is the associative property. So with the associative property for addition, we know that a plus bracket open b plus c is equal to a plus b plus c. So with this, you can prove it with numbers. If they ask you to prove this, you can take any of the natural numbers and prove it, and actually you're going to get the same answer. And for the multiplication, we have that a bracket open bc is also equal to ab bracket open c. And this is what? The associative property. Associative property under addition and multiplication. We also have the distributive property, which is a plus, that is a bracket open b plus c is equal to, multiply this by, you're going to get ab plus, multiply this by, you're going to get what? AC, which is what? The distributive property. And when it comes to the multiplication, we have the same thing as a bracket open plus b c is equal to AC plus what? BC. And this is for distributive property. Distributive property. Now let's go to the last one, which we're going to talk about is the commutative property. And with the commutative property, you know that a plus b is equal to b plus a. When you take any number or any element from the natural numbers and you prove this, you're going to get it correct. And when it comes to the multiplication, you know that a times b is equal to b times a. And this is the word commutative property. The commutative property. So these are the properties under natural numbers, and let's take note of that. Now we are moving on to the next number system, In this case, what you're going to talk about is integers. So the second one we're going to talk about is integers. Integers. Integers, which is second. So for integers, considering subtraction and division, we extend the set of natural numbers to the set of integers. So we have 1, 2, 3, 4, and we have -3, -2, -1, 0, 1, 2, 3, and it goes 1, 2, 3, right? So the set of integers are closed under addition, multiplication, and subtraction. Let's take note of what I'm saying, the closed thing. So for the set of integers, it's closed under what? Addition, multiplication, and what? Subtraction. Which means that when you take any of the integers and then you add them, you should get an integer. When you take any of the integers and you multiply them, you should get an integer. And when you take any of the integers and you subtract them, you should get what? An integer. And then we have some various properties under integers, which the first we're going to talk about is the associative property, which is the same as what I did for the natural numbers. We also have the commutative property. The commutative property, what I also did, commutative property. We have the distributive property, which is the third one, distributive property. And we have the identity. So what you have not done is the identity element. The fourth one is the identity element. Identity what? Element. And in that case, let's prove it, which is a plus 0 is equal to 0 plus a, which is equal to a. And also we have another one, which is a times 1 is equal to what? 1 times a, which is all equal to what? A. So this is the identity element and the properties of integers. We have also the transitivity. It's very important. The fifth one we're going to talk about is the transitivity. 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 Let's take note of that. And with that, for transitivity, we know that if A is greater than B and B is greater than C, then we can say that A is greater than C. It's very simple. Because if A is greater than B and B is greater than C, we can say that what? A is greater than C. That is what? The transitivity property of integers. Let's take note of that. It's very important. The sixth one we're going to talk about is the trichotomy. The trichotomy. Trichotomy. Sorry for the pronunciation. They have different type of pronunciation. That one say trichotomy and trichotomy. So with trichotomy, we have that A being greater than B, comma, and B and A being less than B, or A B equal to. So this is the trichotomy. A can be greater than B, or A can be less than B, or A is equal to B. And the last one we're going to talk about is the cancellation. The seventh property, which is cancellation. Cancellation property. And with the cancellation law, we have that if A times C is equal to B times C, then C should be equal to 0. Then A is equal to B. So if A times C is equal to B times C, and C is not equal to 0, A is equal to B. Is very understandable. So if C is one value, 1, 1, and when you multiply them, then A should be equal to B. As very, and if it's not 0, because if it's 0, all will be 0. That's what they're trying to prove you. So these are the properties under the integers. It's very simple. Third one, we're going to study another system, number system, which is rational numbers. And when we talk about rational numbers or fraction, such as 1 over 3, -2 over 3, ... are rows to permit solution of equation such that bx is equal to a. For all integers a and b, bx equal to a, where b is not equal to 0. This leads to the operation of division or inverse of multiplication. And we write as, so we express this when we make as a subject, we're going to get that A over B. So rational numbers can be expressed as what? A over B, where B should not be equal to 0. That's something that we should note. So that is very simple as rational number. So we could have, if you can express the number as a fraction, then that's number system falls under rational numbers. We have under this, we have another one which is irrational numbers. That is the opposite wise. The irrational numbers, in that case, with irrational numbers, you can't express it as A over B. That means that X cannot be equal to A over B. And for such example, we have like root 2. And root 2 is an irrational number because you cannot express root 2 as A over B. That is what you should know about it, right? It's very simple as that. That's what you should know. And also, remember that every rational number may be expressed as either a terminating decimal or as a reoccurring decimal. Let's put that in our head. So for example, we have 1 over 2, which is what? 0.5. It's a terminating decimal. We also have recurring number 1 over 3. We can express it as what? 0.3333. This is what? A rational number. That's what you need. Again, every rational number can only be expressed as non-terminating or non-occurring. So for irrational numbers, it's what? Non-terminating or non-occurring. But for rational numbers, it's terminating and what? Occurring. That's what we need to know about. That is very important. Let's move on to the fourth one, which is row numbers. And that is the last number system, row numbers. So for row numbers, right, we find that the set of rational numbers, which is Q. So rational numbers, the symbol is Q. The set of rational numbers Q is not closed under the extraction of some roots. In particular, the problem of x squared is equal to 2. The problem of x squared is equal to what? 2. Has no solution x in what? Q. Which Q represents what? Rational numbers. Note, however, that root 2 can be geometrically constructed. Are you getting it? Yes. So we have some operations, right, under row numbers. And under row numbers, we have a lot of operations under row numbers. We have the closure law. And with the closure law, we have it to be A plus B and AB belongs to what? R, which R represents what? The row number system. And also we have the commutative law of addition. A plus B is equal to B plus A. We have the associative property, which is proved in the row numbers, the natural numbers. We have the commutative property. We have the distributive property. We have the identity under addition, which is A plus 0 is equal to 0 plus A, which is equal to A. We have the identity element under multiplication, which is A times 1 is equal to 1 times A, which is A. We have the inverse under addition and multiplication. So the inverse under addition and multiplication is that inverse. We have A plus X is equal to X plus A, which is equal to 0. And we have the inverse under X, which is A inverse, which is mean that A times A inverse is equal to A inverse times A, which is equal to what? 1. We should note this. That is the properties under row number system. So it's very important. And any set such as R, which satisfies the above rule, is called a field. So if any set satisfies the properties of a row number system, is called what? A field. Let's take note of that. It's very important. Yes. So this brings us to the end of the introduction of number theories.